Okay, so we were doing construction of the virtual class. Last thing we ended up with was, what is the deformation obstruction complex? So it is a complex E dot together with a morphism to L dot of the space, such that it captures, similar to the cotangent complex and isomorphically to cotangent complex, deformations completely the same way. So H0, by the way, sometimes for cohomologies in derived category, you can use small letters. So I use this one too. So H0 of phi is an isomorphism, and H minus 1 of phi is a epimorphism or surjection. Okay. So it's for some E dot in the bounded derived category of that space. All right, now whatever that space is, if it is a variety, if it is a scheme, if it is a anything you want. Okay, now if E dot is a complex of arbitrary length, if it is of arbitrary length, then let's then following Berend and Fantecchi, we can construct Picard, what is called Picard stack of E dot, which is basically the following thing. This is the complex, all right? So what you do is, if let's just say that E dot has kind of representation this way. So E dot is some E0, so this is my E dot. So E dot has E0, goes to E1, goes to E2, goes to E minus 1. Let's call this map F. Let's call this map G. And it might go from left or right some number of elements. But the whole point is that we are interested in perfect complexes at the end. But for now, I'm not assuming, I'm not making such assumption. So we are interested in 0 and minus 1. Why are we interested in 0 and minus 1? Because we are interested in deformations and obstructions. Okay, so Picard stack of this complex is actually written as H1 minus H over H0 of E dot. And this notation means you take the kernel of the map G and you divide it by the co-kernel of the map F. So that's exactly what it is. Okay, so it's H1 happens in here. It's the kernel of this map divided by image of this map, and in H0 you can see kernel of this divided by that. But the quotient between the two is going to be kernel of this map divided by image of it. Co-kernel of F. Co-kernel. Okay. So parent and function, and this is a stack quotient. In the sense of in the sense of parent and quantic. Okay. PF shows that H1 over H0 of L dot of M, cotangent complex, is isomorphic to N of M, which is the virtual normal sheaf of M. Remember what the virtual normal sheaf of M was. Locally, you can think of M being embedded inside the smooth ambient spaces. We call that W. That embedding has an ideal. And that ideal produces for us summing of symmetric algebra, some affine space, which is like that. Yes? And if you remember, this was the normal sheaf of M inside ambient space, and this was getting mapped onto something. So a spectrum of this thing is normal sheaf, and this was getting mapped onto something. It was generating all possible ik plus 1. Because this thing is being generated by I1 divided by I squared, the whole symmetric algebra generates the whole sum over all possible k's. Because this map is surjection, if I take the spectrum of this thing, the affine scheme we get out of this injects into the affine space we get out of this. This was the intrinsic normal cone of M, and this is the intrinsic normal sheaf of M. And what we made us be able to say it's intrinsic is that this construction did not need to depend on ambient embeddings, right? Okay, so which we obtained actually by taking these quotient to stack. Okay, a deformation obstruction theory or complex is perfect if H1 over H0 of E dot, which is what I have just defined, is a smooth over M. Okay. So here is how the construction goes. So you have E dot getting mapped to L dot of M. Let's say you have assumed that you have found such a thing. Then, oh, by the way, this is the dual. This by definition is the dual. Then you can dualize in derived category of M, and you will get L dot dual of M getting mapped to E dot dual. Okay. Then from here you can see that H1 over H0 of L dot dual of M gets mapped to H1 over H0 of E dot dual. Okay. Then from here you can actually see that virtual cone of M. So then we can see that what is this thing? This is the virtual normal sheaf of M. And on the other hand, virtual normal cone of M embeds inside here, right? This is the virtual normal cone of M. Virtual normal cone, right? And this is the virtual normal sheaf. And this comes from here. But virtual normal sheaf itself goes from embeds inside here. So from here we can actually see that virtual normal cone of M injects inside virtual normal cone of M, virtual normal sheaf of M, and that injects inside H1 over H0 of E dot dual. Okay. All right. So this thing, in some sense, sees the obstructions whose vanishing is required to have flat deformations. This one. Okay, so I'm going to write it down. So let us assume E dot is quasi-isomorphic to a two-term complex of vector bundles. So I want to have E dot quasi-isomorphic to E minus 1 to E0. Then if I dualize, E dot dual is going to be quasi-isomorphic to E0 dual to E minus 1 dual. Okay? You can assume that E0 dual captures deformations and E minus 1 dual captures obstructions. Okay. All right. So this captures deformations. This captures obstructions. Then I can actually show, because these are vector bundles, H1 is H1 over H0 of E dot dual is the stacky quotient of this by this, because now it's a stacky quotient and it's just two terms only. So if you divide kernel of that map is the whole space here, and the co-kernel of that map is the whole space in here. So it's going to be E minus 1 dual quotiented by E0 dual, the stacky quotient. Okay. So the Picard stack is going to be that E minus 1 dual divided by E0 dual. Okay, on the other hand, via the communication of cotangent complex with the deformation obstruction complex, we know that normal sheaf of M, normal cone of M sits inside normal sheaf of M sits inside this Picard stack. So we actually see that you have, you get a diagram. On the top part of the diagram, you have E minus 1 dual. At the bottom part of the diagram, you have taken quotient of this thing. So there is a natural projection map, quotient map, which actually takes you to this E minus 1 dual divided by E0 dual. Then at the bottom part of it, you have intrinsic normal cone of M. So what you can do is you can take the fiber product of these two things. So this would be cone of M times with E minus 1 of dual over the Picard stack. This is the Picard stack. So this is H1 over H0 of E dot dual. So H1 over H0 of E dot dual. Okay. So what does this Picard stack, this fiber product do? It realizes normal Gromov-Witten sitting inside obstructions, such that the obstructions modulo certain equivalence of deformations. Okay. So if you remember, when we had the bundle, we had a section of that bundle, and we constructed the cone. We constructed class of the cone, and we intersected class of the cone with the 0 section of the bundle, right? This is the cone sitting inside the ambient space, and I have the 0 point in here. So all I need to do, I need to basically intersect with the 0 section of this one. So let's call this map something F. This map F. Okay, if that I call F, then this gives a definition of virtual fundamental class of M as the following. So I need to intersect this with the 0 section of obstruction bundle. So I would look at F of the class of this fiber product over H1 over H0 of E dot dual, and I intersect it with S of E minus 1 dual, where S is M from M to E minus 1 dual is the 0 section. 0 section. And I call this class the virtual fundamental class. Okay, basically this is the definition. So you have the deformation obstruction complex. You're looking for the perfect object so that it has only 2 cohomologies. If it has more cohomologies, it has more terms, you know what the definition of Picard stack of it is. But if it has only 2 cohomologies, you can show that it's quasi-isomorphic to a complex of vector bundles. One of them captures deformations and the other one captures obstructions. So you would like to realize M sitting inside the obstruction bundle with compatible deformations. What would you do? Out of this complex, you construct that obstruction bundle. You dualize it, and you calculate H1 over H0 of the dual. That's the Sestaki quotients. Yes? So think about this Sestaki quotient. The Sestaki quotient, think about groups. If I took modding out by group, but the Sestaki quotient is a different thing. But think about taking quotient by group also. 2 elements in here are different by deformations. If the difference of 2 elements is 0, right? So if the obstructions are vanishing, basically that's the set of equivalences of deformation. So this makes a lot of sense intuitively. Taking this modulo that basically tells you whenever obstructions vanish, you have flat deformation. Then by construction, the fact that obstruction complex maps to cotangent complex, we just showed that intrinsic normal cone of M injects inside this one. And this is actually really because of the embedding of here. So this was result of this basically. Normal sheaf of M, which is H1 over H0 of L dot, dual. Because E dot maps to L dot, with isomorphic deformations and with bigger obstructions, then you can actually show that after dualizations, H1 over H0 of L dot embeds inside here. H1 over H0 of L dot, you can show is the normal sheaf of M, which was sum of the symmetric K products of I mod I squared, as you realize M inside ambient space. And this is a spectrum of this thing. And the cone of M, which is the spectrum of the sum of IK mod IK plus 1, sits inside here. So you get this composite injection to that. Then you realize them as sitting inside E minus 1 dual as a space. That's the fiber product. So you look at the class of this thing, push it into the bundle, and intersect it with the zero section, which is the M. And that's exactly virtual class of. Yeah.
So what's the definition for H1 over H0 for complex?
So we showed it. So if you have something like if E dot has representation like E minus 1 goes to E0, goes to E1, goes to E2, and so on and so forth, arbitrary length. And this is F, and this is G. You look at the first cohomology and the zero cohomology. So H1 over H0 of the complex is going to be kernel of G modulo co-kernel of F. But if the complex is perfect and it's always quasi-isomorphic to a two-term complex of vector bundles, you realize kernel of G is all of E minus 1, this term. The co-kernel of F is all of this term.
So you mean the representation means we have
you have a quasi-isomorphism to a complex of vector bundles.
Perfect.
Yeah.
Term
Exactly.
On the negative one.
That's right. So that's what the definition of virtual class is finally. Okay, now computation of virtual fundamental class, VFC, in some examples. Recall a smooth projective variety X is said to be convex if H1 of C F star of T of X is equal to 0 for any genus 0 stable map F from C to X. F is called convex if for any rational curve, genus 0 curve inside X, pull back the cotangent or tangent bundle of X, you get 0. Okay, so that's good. So we saw that convexity implies the smoothness of the moduli space. If X is not convex, then you don't get that smoothness, but for M0n you might. So assume X is convex. Okay, then M bar 0n x beta is an orbifold of expected dimension. expected dimension. In particular, the fundamental class of m bar 0 and x beta, just the fundamental class itself, which is an element of homology of m0 and x beta with rational coefficients, is the class representing them, right? In particular, we have this, and being convex implies that m bar, this m bar is unobstructed, and hence one can reduce the construction of virtual fundamental class to a trivial intersection of m bar 0 and x beta, yes, in a trivial bundle. It's a smooth, so you can just use it's a smooth space sitting inside a nice bundle, trivial bundle, because obstruction bundle in this case is actually, obstructions are 0. So m is naturally a trivially sitting there. So if I did that, then I will just get what I'm expecting to get. So then, in that case, the virtual fundamental class is going to be equal to the fundamental class. The space is unobstructed. The obstruction bundle is trivial. So m is sitting inside this trivial bundle as itself. It's of expected dimension. So the section of the obstruction bundle, because the whole thing is trivial, the zero locus of that section is all of m. Yes, so intersection of that section with m is all of m. So the virtual fundamental class, the part of m which has expected dimension, is all of m. So that's the fundamental cycle of it. So that's basically the first example. Quintic threefold. Okay, let x sitting inside P4 be a smooth quintic threefold. Okay, let D be bigger than 0. When I say smooth quintic threefold, it means that in the 5 homogeneous variables of P4, I'm looking at a polynomial with homogeneous degree of 5 in that 5 coordinates. So x0 to x4, for instance, example, x0 to the 5th plus x1 to the 5th plus x to the 4th to the 5th equal to 1 or something like that. Okay, so that's a quintic. That's like, in fact, this is Fermat quintic because the polynomial looks like Fermat's equation. But then any other homogeneous configurations of x0 to x4 of degree 5 is a quintic. So because the canonical bundle of P4 is -5, O -5, and the degree of the surface is 5, canonical bundle of this variety is O. Normal bundle of X inside P4, because it's a hypersurface, it's a line bundle, and it's going to be having the degree exactly equal to the degree of the polynomial that defines it. So it would be O of P4, O of X, degree by 5. It would be O of P4 twisted by 5. Okay? Restricted to X. It would be O of 5 restricted to X. That's the normal bundle. Okay, but then canonical bundle of P4 is O of P4 minus 5. There is a formula. Canonical bundle of X is the normal bundle of X times canonical bundle of the ambient variety. Here it's going to be P4, so it's going to be O. Restricted to X. So it's going to be just O of X. So canonical bundle of X is O of X, therefore this is the Calabi-Yau. Calabi-Yau threefold. If you put in degree 3 surface inside P2, same. It's going to be Calabi-Yau variety inside P2. But hypersurface of P2 is one-dimensional. So Calabi-Yau variety inside P2 is what? Elliptic curve. And it's true, elliptic curves are given by homogeneous equations of degree 3. You know that. If you put degree 4 surface inside P3, that will be a quartic in P3, and that's also Calabi-Yau surface, and that's a K3. So it keeps going like that. Okay, so if X is a Calabi-Yau 3, a smooth quintic threefold, let D bigger than 0, goal is to construct this thing. Construct or compute M bar. I'm going to make it easy. M bar 0, 0, XD. Virtual. When I say D, I really mean D times class of a line. Degree D maps from a line into the ambient space. So sometimes to construct these virtual classes, you can actually look at how the space is sitting inside ambient spaces that we understand better. For instance, note that M bar 0, 0 XD sits inside M bar 0, 0 P4D. Because X is inside P4, if I look at degree D lines, degree D maps from lines to X, those sit inside degree D maps from lines to P4 as an embedding. Okay. Let S be a section of structure sheaf of P4 twisted by 5. This is a line bundle whose meromorphic poles has meromorphic poles along our hypersurface. Yes. This is the line bundle which is exactly in one-to-one correspondence with X, the divisor sitting inside P4. This is the normal bundle. This is the one whose restriction to X is the normal bundle. Such that, so look at the section such that restriction of this section to X is equal to 0. Now consider the functor f of S I want to think of this as F's from C to P4 such that F is genus 0 stable maps into P4 with the condition that pullback of this S is going to be 0. So this I would like to call this something else. Maybe I can call this thing big S. So I define a moduli function such that over some scheme S parameterize a set of isomorphism classes of maps to P4, genus 0 stable maps to P4 such that if I pull back section of this bundle, it vanishes. Okay. Modular isomorphisms. This I would like to define this modular isomorphism. Isomorphism of the stable map. So this is now a modular function. Okay, and in fact, f of s is the, actually, you know what, in terms of, because this section, I can call, okay, so I can call this thing, because it depends on this section, so I can call this thing f of little as blank, like that. It's the functor which gives you stable maps to P4 with this condition determined by the section of line bundle on P4. So let's call it this one. Okay. So makes this, because this is very confusing, and so I would like S to be small s, the section of this line bundle. Okay. So not all of the curves, but the curves that satisfy this property given a section of the line bundle. Okay. So in fact, f of s is the functor associated to m bar 0, xt. This is exactly what those are. Okay. And so because this basically just gives you the locus of curves in P4 that lie inside of it. Okay. Hence m bar 0, xt sits inside m bar 0, P4D. Now let V of D be a rank equal to 5D plus 1 vector bundle over the stack M 0, P4D such that V of D restricted to a map fiber of this bundle over this stack is isomorphic to A0 of C and pullback of O of P4 twisted by 5. So I'm constructing over this stack that parameterizes genus 0 stable maps with no markings to P4 a vector bundle. And this vector bundle, fiber was over every point of the moduli space, is given by vector space. And the vector space is space of sections of pullback of this line bundle to C. Okay? So as I vary C, I get a local system. And that's basically my vector bundle. Okay?
So you restrict a vector bundle on.
So I have a vector bundle on the whole moduli stack.
Yeah.
And its fiber over point of the moduli stack is the
fiber. Okay.
is the fiber. Okay? The section S in O P4 twisted by 5, defining X induces a section, let's call it S tilde, in space of sections of M00 P4D with this vector bundle. Okay, and definition of our moduli functor let's call this moduli functor something. I call it star. This moduli functor implies that this stack M00XD is actually isomorphic to the zero locus of this induced section. Right? So it kind of makes sense, right? X is defined as the zero locus of a section of this line bundle. You look at curves inside X, and you look at curves inside P4. Now, the moduli space of curves inside X, you're trying to think of as the zero locus of a section of a bundle. So you need to cook up that bundle. In order to cook up that bundle, you know that this thing sits inside here. So as you ask yourself, is there a bundle in here, supported in here, with the section, whose zero locus is this space? So you're kind of thinking of a bundle, V of D, and this base of your space is M bar 0, 0, P4, D, and then this natural section of this bundle, you call it S tilde, and this section vanishes at certain loci, and you would like this to be M bar 0, 0, XD. So you need to construct what bundle it would be. Well, it's the bundle whose sections are exactly pullback of this to the curves. Now by construction, because X is defined by the vanishing of that section, this realizes the moduli space of curves in P4 with that vanishing to be equal to the moduli space of curves inside X, because X is the hypersurface along which exactly that section vanishes. So vanishing of that section induces, vanishing of S tilde induced section in the level of the moduli space. Okay, so now it is not bad because it's the situation that we had before, and now you have a bundle, you have a zero locus of a bundle, M is sitting inside here, so you can construct a virtual class of this in terms of the virtual class of the ambient space. So, okay, so the zero locus of the induced section, so remark, maybe, yeah. So remember that this is only true for m bar 0, 0, by the way. Genus Gn doesn't work. You lose the smoothness and everything. These are examples. Okay, so here's a remark. In more generality, we may use the stack so maybe I shouldn't put this remark actually. So I think this is already spelled out on this other blackboard. So okay, we are using the stacks. So all right. So then the normal cone construction, which we discussed before, discussed above, gives us the pullback via this section of the normal cone to Z of m bar 0, 0. P4D. And Z is here, m bar 0, 0 xt. And this S tilde again is in the space of sections of m bar 0, 0 P4 D of this vector bundle, suitably constructed vector. Okay. The claim is that the virtual cycle of m bar 0, 0 xt is going to be exactly equal to S tilde pullback of this normal cone of Z. C of m bar 0, 0 P40. Okay. So you look at m bar 0, 0 P4D, and on the low, so it has a vector bundle, suitably constructed vector bundle on it. On the loci, where the section of the bundle vanishes, you look at the kind of the normal cone. So this normal cone sits inside restriction of this bundle over those loci. You can construct a class of the normal cone inside here. And then you would like to take that class and intersect it with the base. This we showed before. We showed what we can do. You construct this class, and you would like now to intersect it with the base. The base is m bar 0, 0 P4. So what do? There is a section map from here to this VD. You take the class in here, because this class is sitting in the homology theory of the bundle, and then you pull it back to the base, so they intersect it with the base. Yeah. And as you do that, the degree of this class will be less because you're intersecting. So this would be whatever this dimension of this thing is, or degree of this thing is, minus the rank of the vector bundle. And that's exactly the expected dimension of it. Right? So in some sense, you're constructing Euler class of this vector bundle. Euler class is the class of the vanishing locus of the vector bundle. The vanishing locus of the vector bundle is the moduli space on X. So that's what you're doing. So here we could do everything because we are doing 0, 0. Okay? So I didn't even need to, and everything is smooth. I didn't even need to, this is a smooth in particular. So I did not even need to construct the deformation obstruction complex or anything. I could capture it from M00P4. And why did I choose M00P4? P4 is a convex variety. So when I use 0, 0, it's a smooth space, so it's nice. Okay, so that's basically that. So this claim was proved by Li and Tian, which was proved by Li and Tian. So I can show you a little bit of this proof. So as you see, now the virtual class of M has its own construction coming from deformation obstruction complex. But this was a very good shortcut. This idea that we just did in here, realizing the zero locus of a bundle, is the thing that we did 2 sessions ago. And the virtual class is the one that we actually constructed today and based on last session. They proved that these 2 constructions match. So how does the proof go? So a sketch of the proof. One shows that this pullback of the fundamental class of cone of Z inside M00P4D is the virtual fundamental class of perfect deformation obstruction complex given by kernel and co-kernel of the, so I have this 2-term complex. As I mentioned, deformations and obstructions are cohomologies of a complex. This complex is 2-term only. It has only kernel and co-kernel at each degree. This is that complex. So it's the complex which is tangent bundle of M00P4D restricted to M bar 00 XD, and then V of D restricted to M bar 00 XD. Okay. It suffices to show that the kernel and co-kernel of this map of this star coincide with the moduli functor Ti of M00XD. Remember the tangent functors? Tangent functors where at each point of the moduli space gives me the vector spaces which parameterize deformations and complex and the obstructions. Which was what? Which was of something at the point F from C to X, which was xi deformation space and obstruction space, xi pullback of the cotangent bundle of x to so yeah, so it should be omega c basically, and then O of c, xi O of c. So this tangent functor was a functor that depended on how you extend your parameterizing scheme. You had S, you extended to S of n, and the kernel of this extension was the thing. So the tangent functor was giving you a x group, which we're telling you how this extension is being done. So for any such n, the tangent functor gives you exactly how the space of deformations are. And I was from 1 to 2. Deformations and obstructions, right? This is what we had before. Okay. Okay. So if let f in from C to X be a stable map over S, the parameterizing scheme. So it's a family of stable maps. Okay. So I can write it like this: C over S to X be a family of stable maps over some S. Okay. Then consider the short exact sequence. Which is I can pull back OP4 of -1, -5 to that will be the pullback of omega 1 of P4, and that will be the pullback of omega 1 of X. So via this map, so okay, first of all, where is this coming from? So difference between cotangent bundle of P4 and cotangent bundle of X is the conormal bundle of X inside P4, and that's O of -5. Now I take all this is the basically Euler sequence, and I take the Euler sequence and pull it back to the family, pull it back to C. Yeah. Okay. Now this is giving me a map to omega 1 of C over S, and this is actually also giving me a map to omega 1 of C over S, and this thing will give me a map to 0. Okay. And this part is awesome equality. Okay. So now I can basically construct some long exact sequence of this. Okay. Taking the long exact homology sequence associated to this short exact sequence, yes, we actually see, so one thing I can do is the following. Look, I can call this two-term complex. Remember, this is not bad, right? X groups, right? X groups is pullback of omega x to omega of c. So c is embedded in both of x and p4. So this is appearing in one of those x groups, and this is appearing in the other x group. So this is the one that gives me deformation obstruction complex of M00XD. And this is the deformation obstruction complex of another moduli space, M00P4D. This is the coordinate there. Both of these guys are two-term complexes. So if you really think about it, I can call this one, what did I call it? B dot. And I call this one A dot. And then I have this two-term complex, which is only one term of it is actually non-zero. So okay, it's a derived, it's a triangle, an exact triangle in derived category. So B dot, the two-term complex, maps to A dot. And in the kernel part of it, right, basically, we don't have kernels in derived category, but I can call it kernel, cocone of it. The cocone of that map in the derived category is a two-term complex whose term is sitting in not here, but in here. Let's call this thing sitting in degree 0, 0, minus 1, minus 1. So all I need to do to say that this is only one sheaf sitting and the other one is 0 is writing down here F0 of OP4 of minus 5 shifted by minus 1. So the degree I part of this complex, if you have some complex A dot I shifted, then degree n of this thing is A I plus n. So if this I is minus 1, degree n of this thing is minus 1 plus n. So what is this complex? This complex, degree 0 part of it is minus 1 part of A, original thing. And degree 1 part of it is degree 0 part of original thing, which is 0. So it's exactly what we have, right? So I just need to, if you are mapping complexes, you need to respect the shift. Okay, so that's that. So now I can think of this as the exact triangle in the derived category. And then from that exact triangle, so I look at the short exact sequence, I see that derived categorically is a map of complexes like this. And now this induces for me a cohomology sequence. So how is this? I can apply short exact sequence. So I can apply Artan, apply Artan O of C to this exact triangle. And it starts from here and it keeps going. Okay? So it gives you Artan A dot OC goes to Artan B dot OC goes to Artan this term F0 of OP4 of minus 5 shifted by minus 1 OC. Yes? Because this is a contravariant coordinate of this Artan functor, you can put the shift outside. If the shift comes outside, it becomes positive 1. Okay, so now I have this exact triangle, and I can look at the sections of this exact triangle. So if I can start from here, so in the level 0, I see harms, so that's x0, whatever a dot is. A dot is pullback, omega x2, omega 1 of c over s OC. Then I will see x0, pullback of omega x to omega p4, sorry, omega of p4 to omega 1 of c over s, OC, yes. And then I can see next term will be, so this is important, right? So let me see, make sure about something. First, I see that term, correct. But then this gives me an x1 term. Is there any mistake here?
What do you think there's a mistake?
Then in the level of x1, x1 goes to x1 goes to x2. That's not what I like. At least what I have written in my note doesn't match with what I have written in here. But let's understand this thing. Did I make a mistake? Wait.
To take the degree 0 terms, you get
Degree 0 part of that complex.
the third term.
The cocone. The cocone. Wait. So I have OP4 of -1, -5, and 0. This is degree 1, this is degree 0. Okay? If I call this one complex x dot, for instance, x dot shifted by -1 is what? X dot shifted by -1 is a new complex. Y dot 0 is x dot of 0 minus 1. Degree 0 term of this is exactly OP4 of -5. And y dot 1 is x dot 0, which is 0. No, that's correct. Let's see. So what am I trying to do? So So if I continue with this process, I will get x1 OP4 minus 5O then I will get x1 f star of omega x omega CSOC, x1 f star of omega p4 omega CSOC, and then over here I will get x2 so p4 minus 1 O. Okay. And question is whether this is actually, and then the next term is x2, right? So the next term is x2 f star of omega x2 omega c over SOC. So this is actually going to be obstruction space of m bar 00xt. This is the obstruction. And this is going to be the deformation of m bar 00xt. Okay, so these are those groups. And then they communicate with the rest of the sequence like that. But I think there must be a mistake in here because first of all, these other terms are going to be vanishing. So this is 0. These are going to be 0. But in particular, I would like to have 0 in here. And this is O of C, by the way. Okay, so this term I want to vanish, but I don't see why. And I think that if I put the shift by 1, it actually helps that. If this thing, I think this should be shifted by 1. If you put the shift by 1, you will have x0, x0, okay? And then in here, you will have x minus 1. Because if your shift is 1, then this will be shifted by minus 1. And then because these are two sheaves, negative x between two coherent sheaves is always 0. Doesn't make sense. So this will go away. And this fixes my calculation. So then I will have this. And this is all I care about. So this would be x2, and I would like to have x1.
What is that? Why is certain term is about the pullback?
And this one is also vanishes by convexity.
So right there is the twisted boundaries.
Yeah.
On P4. Well, why not? But here, there is
Which one?
the third term.
Oh yeah, this is the pullback. This is the same. This is the same, and this is the same. Yeah. Okay. So this x1 starts from x1, then goes to, oh, this is, by the way, x1. And then that is x2, and this should be x0. So this would be pullback of V of D to C. Okay. Yeah. And then the rest will be 0. Yeah, I think that that's the problem. So you need to shift it by 1. So this is correct. Now I understand it. Think of this sheaf as a complex sitting in degree 0, right? Complex sitting in degree 0. Is this complex this complex? It's not. This is a complex which has that term sitting in degree minus 1. This is degree minus 1, degree minus 1, degree minus 1, degree 0, degree 0, degree 0. So I'm constructing a complex in here, which I say this is that complex, but I need to recover from this what I have over there. So that is this complex shifted, right? In a way that this term sits in degree minus 1. You need to shift by plus 1. Right? F0 OP4 is a complex x dot. It is this complex. Minus 5, whatever. Sitting in degree 0, nothing else. Sitting in degree 0. This complex is a shift of that complex. With what number? With 1. Why? Because if I look at the minus 1 degree, minus 1 term of this thing, it's going to be that complex minus 1, degree 0 minus 1, right?
Yeah.
Minus 1 term of this complex is going to be degree 0 original complex. So it's correct. Okay, so you see, okay, now calculation tells us. So this should be shifted by 1. And then this shift by 1 will induce shift by minus 1 in here. And then, yes, now it makes sense. Okay? So I care about x1 and x2. This term is actually equal to 0 because this is negative x. So I only care about this part of the exact sequence. Because that map is already 0. Okay? So this goes to x1, x1, and then this is x0. And this also makes sense because this is the pullback of the vector bundle VD to C. Okay? And that's that. Okay, good. Now, much better. And the rest is by convexity. This 0 is by convexity of P4. By convexity of P4. Next term is going to be having pullback of the omega of P4. And that by convexity of P4 vanishes. Okay, good. You see, one little mistake can actually somehow create problem. Okay. Just shift, mistake by shift. All right, so in my notes, actually, this is put wrongly. I needed to fix it. All right, it follows by exactness of long exact sequence of cohomologies that kernel of this map, that kernel of the map from, we called it the map star. So this map is star T M00 P4D restricted to M00XD VFD restricted to M00XD. This is going to be X1 C over S, pullback of omega X to omega 1 of C over S O of C, or O of C over S. And the co-kernel of the same thing is going to be the X2. Now, think about it. Why? X1 is the deformation space, right? All of these things are in cohomology sequences which we obtain after pulling back to the moduli space xt. This is the deformation space of, this is the tangent space of M00 P4D restricted to M00 xt. And this is the restriction of VD to M00 xt. Because this actually sees the normal bundle. Okay? So what is this map? This is star. This is the map of star. Because this map is exactly the map you're looking at. What sits in the kernel of this map is this X group. So this here, this negative X, this shift, makes this last term right before that equal to 0. So now X group is the kernel of a star map. And this long exact sequence shows it. And the convexity of P1, P4 actually shows us the co-kernel of that map is the term that comes next. And that term is exactly co-kernel of a star. Isn't this nice? So the kernel, co-kernel are exactly the deformation abstraction complex of M0xt. Cool, right? So embedding M0xt inside M0P4D as a zero locus of a bundle VD induces for you exactly same deformation and abstraction space which you knew from before from the very construction of this moduli theory, from tangent functors, tangent abstraction functor. Okay, so this is that map star. Okay, but this is a beautiful proof, right? And I think that's why I think the paper was amazing, really. It's very smart. So, okay. Yeah, so okay, so very nice. I have written it. I just need to fix the shifts. So actually, before, because I'm gonna give you guys these notes as well, even though I'm advising that you always write in the notes. Let me see. Do I have it? Oh, I need to. Okay. Fix this shift. So where is it? This needs to be +1. Oops, why is so big? Yeah. +1. And then this would be, yeah, that's it. Interesting. Yeah, otherwise the whole proof will collapse. Okay. Remark. Oops. I think we ran out of this one. Okay, so remark. The bundle VD and Euler class of VD, Euler class, are defined only on the stack M00 xt and not straight M00 xt. These were the smooth stacks. Everything we did was on the level of the stack. So yet the virtual fundamental class is defined in Chow homology of M00 xt. This is because Euler class of the vector bundle can be pushed forward to M bar 00 xt, to the underlying course modules. You have this push forward of classes. Here's another remark. Let I from the stack M00 xt to the stack M00 P4D be given with the canonical embedding, with the natural embedding of the stacks. Yes. So then push forward of the virtual fundamental class of the stack is going to be the push forward of the pullback by dissection of the fundamental class of the cone of M00 P4D inside the vector bundle VD, which is the one that we defined. And that's going to be, because you're pulling back via the section of the bundle, that's going to be seeing the top term class of the bundle. This will be C to the 5D plus 1. This was the rank of VD. C to the 5D plus 1 of VD intersected with fundamental class of M00 P4D. And this is exactly the one that we showed, that if you have a smooth space with a bundle on it, then you intersect with the intersect the locus, intersect with the class with the zero section, then this is exactly what you do. This is just the intersection theory computation. That's it. So that's basically says the degree of the virtual class of M bar. Take the dimension of this minus 5D plus minus 1. And that has to do with your whatever degree of the curves are. Degree 1, minus 6, degree 2, whatever, minus 11, and so on.
It should be a
Compactified version, yes. Absolutely. Compactified version. Okay. So we started at 9:15. How much time do we have?